All right, so last time we discussed quantum gradients, higher order gradients, and the like, and this is just implementing them in Pennylane. So this is the quantum gradients 100, 200, and 500 challenges for the QHack hackathon. So if we remember, if I go back, share this, we can see that for this first problem, quantum gradients 100, it gives us the definition of the gradient or the derivative as presented here, and all we have to do is calculate this gradient in Pennylane. And so going over to the code, we can see it provides us with this circuit, some Rx, Ry, Rz gates. Doesn't matter the type of gate, the action is the same. And we can see that we can see exactly this equation put into practice here. So we just create a copy of the weights, then we go through all of the weights, we add pi over 2, which is just the S value that I've defined here. You see that a lot in parameter shifts like the Crookes paper, you'll see that. And then you evaluate the circuit with that parameter change. Then I subtract 2 times that parameter because it's added, and so now we're subtracting it away. And then we evaluate the circuit, then we do 1/2, and then we multiply by this evaluation minus that evaluation. And so we can see we calculate this first parameter, we calculate the second one, and then we just do the math, the division and subtraction. And it's really straightforward here. I mean, this could probably be expedited. I guess I could put in, for example, without copying the weights, but even with this excess code, it's only a few lines long, and we can see that when we run this code, I Alt-Tab over, so we run, and we have to take an input, which defines the given weights, the starting weights, because we're not doing any optimization here. Oh, I don't think that's right. Because 1.ends or 1.n maybe. Maybe I have to go check the file now. Oh yeah, it is 1.n. Okay. And so we run the file, we do 1.n. It'll take a second to run. Wow, I have a lot of free space, 300 gigabytes. And when it's done running, we can compare it to the answer that is expected. So we can see they look different just because there's decimal places here, but this value is exactly the same. I'm going to do it for 2 as well. And this is just, so this would be the gradient of this circuit. And so it doesn't really matter what the circuit is. It doesn't really matter what the weights are. We can see these are exactly the same. And so therefore we have the parameter shift correct. And we can move on to the second one. Here we have, ooh, that is not what I meant to do. Here we have parameter shift again, but this time we want to calculate the second derivative, i.e. the Hessian, or to make the Hessian, I should say. And so normally it would require to make that square matrix 4 to the number of parameters squared, because you have to do the gradient, this 2p calculations squared, because you have to make that p by p matrix. However, the challenge here is you have to use exactly 51 evaluations. So for the given, it says somewhere in here that there's 5 weights. So we have to calculate the gradient and the Hessian with only 51 evaluations. So the gradient clearly takes 10 evaluations. Normally, the Hessian would take about 100 because it's 4 times 25, or 5 squared. However, we can reduce it by good choices of S and knowledge of the Hessian properties. So first, before I get into code, let's talk about how we can do the Hessian more efficiently. So we know that the Hessian is this this matrix of partial derivatives. I'm not going to write it out, but what we know from the gradient calculation is, let's just take an arbitrary one over here and arbitrary one over here. So if we have, I'll do and we have these two terms, so across, diagonally opposed on the Hessian matrix. Normally, if we have some arbitrary function, if we just write some random function, if we consider just this function so this two variable function, f of x comma y equals x squared plus y squared, and we can see that the asymmetric derivative, second derivative here, where you take the derivative of x first and then the derivative of y, so you take the derivative of x, you get 2x plus y squared, and you take the derivative with respect to y, the first term would disappear because there's no y in it, and you get 2y. You can see this is not, these are not equal to each other in this case. However, because we know the parameter shift rule from the previous video, I don't really want to write this whole thing out, but I will. We know there's 4 terms, so if we use pi over 2 as our term, we know it's over 4, and there's 4 terms here, and it's theta plus pi over 2 times, and then these are the direction vectors, I, j. So there's plus plus, there's minus plus, there's plus minus, and there's minus minus. And so because we know all of these, we can say, hey, wait a minute, this is symmetric. There's the 4 possibilities. So if we switch I and j, this changes nothing, assuming we use the same S value for both of them. And so we can say, hey, wait a minute, this matrix is diagonally symmetric, or there's probably a term for this. I don't remember my linear algebra, but we're reflecting across this line, these values are the same as down here, because in this case, this is equal, because we know from the formula that all of these values are the same if you swap the position in the weight matrix or weight vector, because all 4 possibilities exist. So what we can do is we can go to the code, and we can see that first we calculate the gradient. So this is exactly the same code as before, and we can see that to calculate the diagonal matrix, or the diagonal values of the Hessian, it isn't exactly the gradient. It's simply you just have one additional value here, which is the starting value. And this is presented in the paper we discussed last time that presents the arbitrary higher order derivatives. So basically we can reuse some of these calculations. And then when we want to make the Hessian, so this is the gradient right here, and this is exactly the same. I literally copied the code from the previous problem. And so the only added value is this Hessian symmetric term, or diagonal term right here. And so when we want to make the Hessian, we iterate through the square matrix, and if it's the diagonal value, we don't do anything. But notice we only iterate through the top right portion of the matrix. So we only iterate on values, northwest or northeast, if you will, of the diagonal. And so the same principle applies. We can see we have this. So we have the plus plus for each weight. We have the minus for weight 1. We have the plus minus, or sorry, this is, so this is actually, this is okay, let me start again. So this is plus plus, this is minus plus, this is plus minus, and this is minus minus. Basically in terms of how we're looking at the subtracting the s term or adding it is what I'm referring to by plus minus. So we have these 4 evaluations, and this is where the 4 comes from, because it would normally be 4 times, and then there's p squared terms in the matrix. However, we're reducing it because we're only doing the top right portion of the matrix, so we evaluate it using the same formula, and then reset the weights. And then for the rest of the Hessian, the bottom left part, we simply copy over these values from the top right part. And so we can see that if we run this code, so we do Python, and then we run the code, and it might take a second to run. We can compare it to the answer. This is going to be a huge output, I think, too, very long. So let me, this might be hard to compare directly. And you can see there's a certain degree of error. You can see this first value right here. It's not exactly the same. Oh, hold on 1 second. Oh, yeah, that's because I was confused. I typed it wrong. Typed the wrong answer. There we go. Now they're the same. So ignore this code. That's incorrect. I typed the wrong value. We can see this is the same. If I highlight this just to clarify, we can see negative 3.0. I mean, you can just do a direct comparison and see that it's correct. And we can also see this is the number of evaluations. There's 51 circuit evaluations. I'm not going to run it for the second input because I don't think that really matters. So now let's go back to the last problem, which uses the Fubini study metric, or basically the quantum Fisher information. So this time the problem is, let's scroll down, we want to create the natural gradient. And so the natural gradient is the inverse of the Fubini study metric times the gradient. And so that's all we have to do, but we do actually have to, they have like a block approximation built in. The QML.metric tensor is, I'm pretty sure, yeah, block diagonal approximation. And so what we do with this, we can see here, when I discussed it in the theory of quantum gradients, which I'm not going over the theory behind this. Like, if you don't understand all these equations and such, please refer to that video. But in this case, if you remember in that video, I said that we could calculate these values by calculating the probability of the 0-bit string, the all 0-bit string. But that was too much work, so to be honest, I did this the lazy cheating way. I mean, not actually cheating in terms of the competition, but cheating in terms of you can't do this on a real quantum device. And that is, if we go over here, so the reason I say it's cheating is because cheating in context of real devices is because I access the internal state vector of the quantum simulator, which you can't do that in real hardware. But in simulator, I can just directly look at the wave function or the state vector, so I have direct access to this term right here and right here. And so what we do is we get the initial state vector. We take the Hermitian, or the conjugate transpose, and then for each value in this, this n by n, or I guess p by p, since they use n parameters here, but p parameters before, is we do the same sort of calculations as the Hessian, the plus, plus, plus minus, minus plus, minus minus. However, this time, rather than caring about the results of this, we get the device.state at the end of each of them, and then to calculate this whole thing, we do 1/8 times this negative, and then we do the square of this this product, this inner product, and then we square it, which is just multiplying by the conjugate, and we add this, add, and subtract. So we add the second term, I scroll over, we add this third term, we subtract the fourth term. And so that'll give us the Fubini study metric, because we're looking at the exact state here. And then we calculate the gradient exactly the same as before, once again, and we invert the Fubini study metric, and they told us it would be perfectly invertible, so I'm not using any sort of pseudo inverse calculations. And then we get the natural gradient by doing the matrix multiplication of the inverse of the Fubini study metric by the gradient. And so that's pretty much it. All of these were pretty straightforward once you know the math and do a little trickery with access to the device.state. And if I run this code on gradient in, you can see it'll generate the natural gradient, which is a length 6 vector, I believe. And we can see these are exactly the same. And so that's it for quantum gradients. I will be doing some parameter shift in TensorFlow shortly. And I will also go over next is the circuit training for the QHack challenge. So I'll go over that next after I do the TensorFlow parameter shift.